So today we're going to be discussing something called molecular polarity. And this is where we tie everything that we've been doing in Chapter 6 all together. And this is going to explain some things like why ionic compounds like table salt are solid at room temperature, but other molecules like water are a liquid at room temperature, and others such as carbon dioxide are a gas at room temperature. And we're going to start with a little refresh of what causes these different types of bonds. So let's take a look at something we saw earlier back in the beginning of the chapter. So this thing called electronegativity, and let's remember that what we're going to call electronegativity, we'll abbreviate it EN, and we'll say it's the pull on electrons. So the higher the electronegativity, the greater the pull, the greater the desire an atom has for an electron. And so if we zoom in here, we've got some little graphics that kind of show what's going on here. That if and it's the difference in electronegativity that does this. So these are what we call delta EN, difference in electronegativity. We have that chart. And if the difference in electronegativity is 0.3 or lower, 0.3 or lower, we're going to call that a nonpolar covalent bond, and that means that the electrons are shared completely equally. If the bond character, the difference in electronegativity is greater, equal to 1.7 or greater, that's what we call an ionic bond. This is what we're interested in when we have difference in electronegativity between 0.3 and 1.7, because that's what we're going to call a polar bond. And if we zoom in even further, we'll see that the atoms in a polar covalent bond aren't sharing electrons equally. They're spending more time around one side of the molecule. That's giving a difference in charge distribution. And what we're saying is that it's not that we've got a negative atom and a positive atom like we have in an ionic bond. What we have here is simply a difference where one side of the atom is relatively positively charged. One side of the molecule is relatively positively charged, and the other side of the molecule is relatively negative. Well, this is pretty simple when it's a molecule that has only two atoms involved. Like, for example, if we knew that this was a bond between hydrogen and chlorine, we would say, well, chlorine's got an electronegativity of 3, and hydrogen has an electronegativity of 2.1. So clearly it's a covalent bond, but the difference is only 0.9, and so it's clearly polar, and the chlorine is more negative, and that's pretty cut and dry. But what happens when we have a molecule with multiple atoms, and what is the overall charge distribution? So let's take a look at a molecule that is an old friend of ours, and we'll see how this works. So going all the way back to the beginning of the chapter, if we were going to ask for the distribution of electrons in a molecule of water, and you were going to draw the Lewis structure, you'd end up with something like this. And this is a water molecule, and it follows the format AB2 E2, which according to our chart is something called bent. And that means that the molecule actually looks like this. And we've got this angle of 109.5 degrees between these two hydrogen atoms. What does this mean in terms of this distribution of charge? Because we also know that the hydrogens each have an electronegativity of 2.1, and oxygen has an electronegativity of 3.5. That's clearly a polar covalent bond. And that means that the electrons are spending most of their time around the oxygen. That means that the electrons are spending most of their time around the oxygen and very little time around the hydrogens. That means that, relatively speaking, the oxygens has a net negative charge and the hydrogen has a net positive charge. What does this mean in terms of the overall shape? So let me get a better picture of this because I cannot draw. So this is what I was trying to draw, and they word this interestingly. We say that the electrons are being pulled towards the oxygen because oxygen has a higher electronegativity. Let's remember that oxygen's electronegativity is 3.5 and the hydrogens are each 2.1. The electrons are being pulled towards the oxygen, and that means that the oxygen side of the molecule has a relative negative charge and the hydrogens are relatively positive. What we're concerned with is that this molecule has a positive side and a negative side. This is what's called a dipole. It means this is the positive end and this is the negative end. Typically, what we do is we draw a small arrow and we make one end of it look like the positive sign. This is what's called a dipole. And for water, it is particularly interesting because it means that the negative end of one oxygen atom, one water molecule, the negative side being the oxygen atoms, is attracted to the positive side of other water molecules because opposites attract. I'll show you what we're talking about. Here is our buddy water. We got all these Mickey Mouse heads floating around, and what's going on here is that there is this molecular dipole, the negative side of this water molecule here and positive side here. We draw it like that. And it means that water has a tendency to stick to itself. So all of you are going to ask if water is wet. No, water is just water. But it's really good at sticking to other things because it has this polarity. And water makes other things wet. So there you go. A chemistry teacher just answered that question. Let's take a look at another molecule that, unlike water, doesn't stick to itself very well. All right, this is what makes water a liquid at room temperature. Other molecules that doesn't work quite so well. Let's take a look at another one. All right, this is a molecule of carbon dioxide. This is a gas. You know this because this is what you exhale. And of course, it's a gas at room temperature. So let's draw the Lewis, and you guys already know how to do that. So if you drew the Lewis, you would get something like this. Okay? Let's zoom in on this. We know that in a molecule of carbon dioxide, we've got carbon, we've got oxygen. The oxygens have an electronegativity of 3.5, and the carbon is 2.5. You can look it up. Okay, these bonds between carbon and oxygen, ignore the double bond part. That's just, we're just keeping track of the electrons. This doesn't have any effect on polarity, any of that stuff. What we do know is that of all these electrons that are involved in a molecule of carbon dioxide, the oxygens have a higher electronegativity. They've got a greater pull on the electrons, and that means that the electrons spend most of their time around the oxygen atom and very little of their time around the carbon. That means the oxygens are negative and the carbon is positive. Let me get a better picture of this because, as you know, I cannot draw. So if we're looking at the distribution of electrons in a molecule of carbon dioxide, we see that there is, even though the distribution is uneven, there isn't any of this molecular polarity stuff, what we call a dipole, because there isn't a negative and positive side. There's a negative end and a positive center, but there isn't what we call a formal dipole. And what's interesting about this is that because carbon dioxide doesn't have one, it doesn't stick to itself very well. So while water might be a liquid at room temperature, carbon dioxide is very much a gas. So as we're going to do this, keep in mind that molecules that have a strong dipole have a tendency to stick to each other. They tend to be liquids or solids at room temperature, and the ones that don't, those tend to be gases. All right? So let's take this for a spin, and best of luck. Let's do one more, shall we? Let's do one more. Okay, this is a molecule called methane. It is a gas at room temperature. Do a little research and you'll find out where it comes from, and you'll see that yes, it is very much a gas. And if you were going to draw the Lewis structure for methane, you would get something that looks like this. And because this follows the format AB4, it is a molecule with the shape tetrahedral. And that means that it looks like this, and when I try to draw it, it doesn't make any sense. We've got a hydrogen coming out towards us and one going away from us. And since I can't draw, here's what it looks like for real. So our question is this molecule polar? I mean, if we look closely, hydrogens have an electronegativity of 2.1. And the carbon has an electronegativity of 2.5. That's a delta En of 0.4, so it lands definitely in polar territory. But is the molecule polar? We can guess that it isn't because it's a gas at room temperature. But let's take a look at the distribution of electrons and in terms of bond polarity, what's going on. So let me get a better picture of this. And so even though we know that the hydrogens aren't really getting the electrons very often, and even though we know that the electrons are spending most of their time around the carbon, it means that the hydrogens all have a relatively positive charge, and the carbon has a relatively negative charge. But they cancel each other out because this molecule is completely symmetrical. And so even though there is a strong bond polarity, there's no overall molecular polarity in this molecule, which might explain why methane is a gas at room temperature. All right? And let's also recall that if we were doing this with a molecule that has a lone pair, something like ammonia, where it looks like this when it's done, when we draw the Lewis structure. This lone pair that goes right here, it doesn't play into the polarity because it's not orbiting a particular set of atoms. And so if we were to draw the polarity for ammonia, it would look like this. Notice how we ignore the lone pair, and that makes this molecule asymmetrical, and that means that the polarity is in this direction, where the hydrogens are slightly more electronegative. They have an electronegativity of 2.1, and nitrogen is 3. All right, 2.1 and 3, and that is going to make our molecule slightly more negative on the nitrogen end, and so the polarity points in this direction. And this explains why ammonia is a liquid at room temperature. We find it in cleaning products, and bleach, and those are all liquids at room temperature. Okay, take this for a spin, and I'll see you on the next one.